We are all accustomed to thinking of solutions as mixtures of a substance dissolved in water. But in fact, the meaning of the term solution is broader than that. Perfumes, antiperspirants, the air we breathe, the alloys we come across in daily life like steel, brass and bronze are all solutions. The utility or importance of solution in life depends on their composition. Body fluids are examples of complex liquid solutions containing many different solutes like electrolytes, sugar, urea, oxygen and carbon dioxide. The importance of the concentration of solutions can be seen from the fact that any change in their concentration can have a significant impact on the living system. For example, 1 part per million or 1 ppm of fluoride ions in water prevent tooth decay, while a concentration of 1.5 ppm causes spotted tooth. And any concentration at and above 4 ppm becomes toxic. Therefore, sodium fluoride is used as rat poison. Intravenous injections are always dissolved in water containing salts at particular ionic concentrations, so as to match the blood plasma concentration. A solution is defined as a homogeneous mixture of two or more chemically non-reacting substances whose composition can be varied within certain limits. A homogeneous mixture is one in which the composition and properties are uniform throughout. In a solution, the component that is present in a smaller quantity is known as the solute or the dissolved substance. The component that is present in a larger quantity is known as the solvent or the dissolving substance. The solution has the same physical state as the solvent. A solution containing only one dissolved solute in a solvent is called a binary solution. Depending upon the physical state of the solvent, various types of solutions that can be formed are a solution in which a gas is the solvent, and a gas, a liquid, or a solid is the solute, is known as a gaseous solution. For example, air is an example of gas in gas type of solution. Chloroform mixed with nitrogen gas is an example of liquid in gas type of solution, while camphor in nitrogen gas is an example of solid in gas type of solution. A solution in which a liquid is the solvent and a gas, a liquid or a solid is the solute is called a liquid solution. Oxygen dissolved in water is an example of gas in liquid type of solution. Ethanol dissolved in water is an example of liquid and liquid type of solution, while glucose dissolved in water is an example of solid in liquid type of solution. These liquid solutions occupy a special place in chemistry, as most chemical reactions take place in solution phase. Similarly, a solution in which a solid is the solvent and a gas, a liquid, or a solid is the solute is called a solid solution. A solution of hydrogen in palladium is an example of gas in solid type of solution. An amalgam of mercury with sodium is an example of liquid and solid type of solution, while copper dissolved in gold is an example of solid in solid type of solution. Out of the various types of solutions we just discussed, the most significant are those that are in the liquid phase. We will therefore confine our study to binary liquid solutions. The concentration of a solution is defined as the amount of solute present in a known amount of solvent or solution. Concentration can be expressed qualitatively as well as quantitatively. Qualitatively, we describe a solution as either dilute or concentrated. When a solution contains a small proportion of solute relative to the solvent, we call it a dilute solution. On the other hand, a concentrated solution contains a large proportion of solute relative to the solvent. This qualitative means of describing concentration, although useful, sometimes leads to confusion, and thus arose the need for a quantitative description of solutions. Quantitatively, the concentration of a solution can be described in several ways. These methods are mass percentage, volume percentage, mass by volume percentage, parts per million, mole fraction, molarity, molality. Let's discuss these methods one by one. Let us first discuss the mass percentage or weight by weight percent method. The mass percentage of a component of a solution is defined as the mass of the component in the solution divided by the total mass of the solution multiplied by 100. It is important to note that as we are expressing the concentration in percentage, it implies that we are defining it per 100 units of the solution. If X grams of component A is dissolved in Y grams of component B, then the mass percentage of A is given by X, which is the mass of A divided by X plus Y, which is the total mass of the solution multiplied by 100. For example, a 20% weight by weight solution of sodium chloride in water means that 20 grams of sodium chloride is present in 100 grams of the solution. Note here that 80 grams of water and 20 grams of sodium chloride make 100 grams of the solution. Another way of expressing concentration in percent is volume percentage or volume by volume percent. The volume percentage of a component in a solution is defined as the volume of the component divided by the total volume of the solution multiplied by 100. The concentration of solutions, where both the solute and the solvent are liquids, is commonly expressed using this method. For example, 25% of ethanol solution in water means 25 milliliter of ethanol is dissolved in 75 milliliter of water, such that the total volume of the solution is 100 ml. Yet another way of expressing concentration in percent is mass by volume percentage. This is expressed as the mass of the solute divided by the total volume of the solution multiplied by 100. For example, a solution of 23% weight by volume contains 23 grams of solute per 100 milliliters of the solution. This way of expressing concentration is widely used in medicine and pharmacy. When a solute present in a solution is in a very small quantity or trace amounts, then its concentration is expressed in another quantity known as parts per million or ppm. Parts per million or ppm is defined as the ratio of parts of the solute to million parts of the solution. Mathematically, It is expressed as the total parts of the component divided by the total number of parts of all the components of the solution multiplied by 10 to the power 6. The concentration can be expressed as mass to mass, volume to volume, or mass to volume. For example, the concentration of dissolved oxygen in seawater is 5.8 grams per 10 to the power 6 grams of seawater and is written as 5.8 ppm. Also, the concentration of pollutants in water or the atmosphere is often expressed in terms of ppm. Now let us discuss another commonly used concentration term, the mole fraction. The mole fraction of a component in a solution is defined as the ratio of the number of moles of that component to the total number of moles of all components in the solution. It is represented by X. Mole fraction is an ideal way of representing the concentrations of various chemical species in a mixture. It is useful for representing concentrations in gaseous mixtures. For example, in a binary mixture, if the number of moles of A and B are Na and Nb, respectively, then the mole fraction of A, Xa, equals Na divided by Na plus Nb, and the mole fraction of B, Xb, equals Nb divided by Na plus Nb. It can be seen that the sum of the mole fractions of component A and component B is 1. That is, Xa plus Xb equals 1. In a solution containing I components, the mole fraction of the ith component, Xi, is expressed as Ni divided by N1 plus N2 plus N3 and so on. It is important to note that the sum of the mole fractions of all the components of a solution is always equal to 1. That is, in a solution of I components, X1 plus X2 plus X3 and so on till Xi is equal to 1. For example, if a solution contains 4 moles of alcohol and 6 moles of water, then the mole fraction of alcohol can be calculated by substituting the values of the number of moles of alcohol and the number of moles of water in the formula. Thus, mole fraction of alcohol equals 4 divided by 4 plus 6, which is equal to 0.4. As the sum of the mole fractions of all the components of a solution is always equal to 1, the sum of the mole fraction of alcohol and the mole fraction of water is 1. Or, the mole fraction of water is 1 minus 0.4 or 0.6. Noted here that mole fraction is a dimensionless quantity. Let us now look at another frequently used concentration term, molarity. Molarity is defined as the number of moles of a solute dissolved in 1 liter of the solution. It is represented by capital M. Mathematically, the molarity of a solution can be represented as M is equal to N. The number of moles of solute divided by V, the total volume of the solution in liters. If Wb grams of the solute of molar mass Mb is present in V milliliters of a given solution, then M is equal to Wb divided by molar mass Mb multiplied by 1000 by V ml. Now let us solve a numerical problem on molarity. Calculate the molarity of a solution containing 10 grams of sodium hydroxide in 500 ml of the solution. The first step is to write the formula for molarity. Then, list the given variables. That is, Wb is equal to 10 grams, V is equal to 500 ml, molar mass M for sodium hydroxide is 40 grams per mole. Now, substituting the values in the formula and solving it, we get M is equal to 0.5 moles per liter. Another very important method of expressing the concentration of a solution is molality. It is represented by small m. Molality is defined as the number of moles of a solute dissolved per kilogram of solvent. Mathematically, it is represented as m is equal to n, the number of moles of the solute divided by the mass of the solvent in kg. If Wb grams of the solute is dissolved in Wa grams of the solvent, then the expression for molality becomes m is equal to Wb divided by the molar mass of the solute multiplied by 1000 by Wa. Let us solve a numerical problem based on molarity and molality. An antifreeze solution is prepared from 222.6 grams of ethylene glycol, C2H6O2, and 200 grams of water. Calculate the molality of the solution. If the density of the solution is 1.072 grams per milliliter, then what will be the molarity of the solution? The first step is to list the given variables. Wb is equal to 222.6 grams. Wa is equal to 200 grams. And the density of the solution is 1.072 grams per milliliter. The molar mass of ethylene glycol is 62 grams. Substituting these values in the formula for molality, we get M is equal to 222.6 divided by 62 multiplied by 1000 by 200. On solving, we get M is equal to 17.95 moles per kg. Next, let us find the molarity of this solution. You will have to calculate the volume of the solution since molarity takes that into account. The total mass of the solution is the sum of the mass of ethylene glycol and the mass of water. That is, 222.6 grams plus 200 grams, which is equal to 422.6 grams. Using the value of density of the solution, which is 1.072 grams per milliliter, you can calculate the volume of the solution. Density is equal to mass per unit volume, and thus V is equal to 422.6 grams divided by 1.072 grams per milliliter, or V is equal to 394.2 milliliter. Now substitute this value of V in the expression for molarity. Therefore, M is equal to 222.6 divided by 62 multiplied by 1000 divided by 394.2. On solving, we get M is equal to 9.1 moles per liter. Each method of expressing the concentration of solutions has its own merits and demerits. Mass by mass percentage, parts per million, mole fraction, and molality are independent of temperature, whereas molarity, volume by volume percentage, and mass by volume percentage are functions of temperature. This is because volume is a temperature-dependent quantity, while mass is independent of temperature. Solubility is the property of a solute to dissolve in a solvent to form a homogeneous solution. Solubility is defined as the maximum amount of solute that can be dissolved in a specified amount of solvent at a specific temperature. Solubility is the result of an interaction between particles of the solute and solvent. Hence, it depends on the nature of the solute and the solvent, as well as on the temperature and pressure. However, note that the solubility of solids in liquids is independent of pressure. Let us first discuss the solubility of solids in liquids. The solubility of solids in liquids depends upon two factors, namely, the nature of the solute and solvent, and the temperature. Let's discuss how solubility depends on the nature of the solute and solvent. It is observed that while sodium chloride and sugar dissolve readily in water, naphthalene and anthracene do not. In general, solubility follows the rule like dissolves like. That is, a polar solute dissolves in a polar solvent, and a non-polar solute dissolves in a non-polar solvent. Therefore, polar or ionic molecules like sugar and sodium chloride dissolve in water molecules which are polar, while non-polar molecules like naphthalene and anthracene dissolve in solvents like benzene and carbon tetrachloride, which are non-polar. This behavior can be explained in terms of the interaction between particles of the solute and the solvent. The solubility of ionic compounds is the result of the strong electrostatic interaction between the ions of the solute and the polar molecules of the solvent. The solubility of non-polar solutes is the result of similar solute-solute, solute-solvent, and solvent-solvent interactions. When a solid solute is added to a solvent, its concentration in the solution increases. This process is known as dissolution. If you continue to add the solute, there will come a stage when no more of the solute can be dissolved in the solvent at a given temperature. A state of dynamic equilibrium is reached between the solute particles going into the solution and the solute particles separating out. Such a solution, in which no more of the solute can be dissolved at a given temperature, is called a saturated solution. Therefore, a solution in dynamic equilibrium with undissolved solute is a saturated solution and contains the maximum amount of solute dissolved in a given amount of solvent. The concentration of the solute in such a solution is its solubility. If any more solute is added to this saturated solution, it gets separated out, and the process is called precipitation. On the other hand, a solution in which more solute can be dissolved at a specific temperature is called an unsaturated solution. The solubility of a solute also depends on temperature. When a solid dissolves in a liquid, a change in the physical state of the solid takes place. Heat is required to break the bonds holding the molecules in the solid together. At the same time, heat is given off during the formation of new solute-solvent bonds. If the heat liberated in the dissolving process is greater than the heat required to break the solid apart, the net dissolving reaction is exothermic, as energy is given off in the process. It can be seen that as per Le Chatelier's principle, for an exothermic dissolution process, an increase in temperature inhibits the dissolving reaction, since excess heat is already being produced by the reaction. For salts like cerium sulfate and sodium carbonate monohydrate, an increase in temperature decreases solubility. On the other hand, if the heat given off in the dissolving reaction is less than the heat required to break the solid apart, the net dissolving reaction is endothermic. As per Le Chatelier's principle, for an endothermic dissolution reaction, more heat facilitates the dissolving reaction by providing energy to break the bonds in the solid. The solubility of most substances like sodium nitrate, sodium chloride, and potassium nitrate increases with an increase in temperature. The use of first aid instant cold packs is an application of this solubility principle. Ammonium nitrate is used in instant cold packs as its hydration is an endothermic process. That is, it requires heat. Therefore, heat is drawn from the surroundings and the pack feels cold. Note that the solubility of solids in liquids is independent of pressure, since solids and liquids do not compress appreciably when the pressure is increased.
Gases dissolve in liquids to form solutions. Generally, gases that are easily liquefiable are more soluble in a solvent. For example, carbon dioxide is more soluble in water than oxygen at a given temperature. Oxygen dissolves in water to a very small extent, about 5 to 10 milliliters per liter of water. However, even this small quantity can sustain aquatic life. The dissolution of gases in liquids is an equilibrium process. At equilibrium, the rate at which the gaseous solute molecules escape the solution equals the rate at which the molecules re-enter the solution. An increase in pressure results in more molecules of the gas striking the surface of the liquid and entering the solution in a given time. Therefore, at high pressure, more gas dissolves in a given volume of liquid than at lower pressures. This proportionality of the solubility of a gas to pressure was first proposed in 1800 by William Henry and is known as Henry's law. The law states that at a constant temperature, the solubility of a gas in a liquid is directly proportional to the pressure of the gas. Dalton, a contemporary of Henry during the same period, concluded independently that the solubility of a gas is a function of its partial pressure. If the solubility of a gas is expressed in terms of the mole fraction, then the statement of Henry's law becomes: the mole fraction of a gas in a solution is proportional to the partial pressure of the gas over the solution. However, the most commonly used version of Henry's law is: the partial pressure of a gas in vapor phase, P, is proportional to the mole fraction of the gas, X, in a solution. Mathematically, it can be represented as P is proportional to X, or P is equal to KHX, where KH is the Henry's law constant. Further, if you plot a graph between P, the partial pressure of a gas in vapor phase, and X, the mole fraction of the gas in a solution, then you will get a straight line passing through the origin with its slope equal to KH. The graph also shows that as P increases, X, the mole fraction of the gas in a solution, also increases. The Henry's law constant, KH, for some common gases and water as the solvent are given in the table here. On comparing the values of Henry's constant for oxygen and nitrogen, we can infer that the value of KH increases with an increase in temperature. As a consequence, the solubility of gases generally decreases with an increase in temperature. Also, if the dissolution of gases in liquids is considered as a process similar to condensation, then it is an exothermic process, where a dynamic equilibrium is established between the gas and the solution phase. On applying Le Chatelier's principle to this equilibrium, we see that the solubility of a gas decreases with an increase in temperature. It is seen that when water is heated, bubbles of gas appear on the sides of the container well below its boiling point. These are bubbles of air, which are evolved when water, which is air saturated at lower temperatures, is heated. It is interesting to note that hot water tastes flat because the oxygen in it has been expelled by heating. Have you ever wondered why aquatic species are more comfortable in cold water rather than in warm water? This is because the solubility of oxygen is more at low temperatures. Let us now discuss some important applications of Henry's law in the industry as well as in biological solutions. Carbonated drinks are packed under high pressure of carbon dioxide, some of which gets dissolved in the beverage. When the bottle is opened, the partial pressure of carbon dioxide above the solution drops. As a result, some of the dissolved carbon dioxide comes out of the solution as bubbles. Henry's law has an important application for scuba divers. The pressure is very high deep in the sea. As a result, the amount of nitrogen dissolved in the blood and other tissues of deep-sea divers increases. If the diver returns to the surface too rapidly, then the nitrogen forms bubbles in the blood as it becomes less soluble due to a decrease in the pressure. These bubbles are dangerous as they can plug small arteries and cause serious damage by stopping the flow of blood to a particular organ. Divers may experience this potentially painful and lethal condition called the bends if they do not ascend to the surface slowly, allowing themselves time to adjust to the lower pressure at the surface. To alleviate this problem, artificial breathing mixtures consisting of 32.1% oxygen, 56.2% nitrogen, and 11.7% helium are used. Helium is 5 times less soluble in blood than nitrogen. As a result, there is less dissolved gas to form bubbles. On the other hand, at high altitudes, the atmospheric pressure is low and there will be less concentration of dissolved oxygen in blood and tissues. Therefore, mountaineers at very high altitudes suffer from anoxia, which is low oxygen supply in the tissues, accompanied by weakness and inability to think clearly. That is why mountaineers carry oxygen cylinders at high altitudes. Let us now discuss the vapor pressure of binary solutions. We shall discuss the vapor pressure of liquids in liquids and solids in liquids. First, we will discuss a binary solution of 2 volatile liquids, 1 and 2, that are completely miscible in all proportions. In 1886, through experimental studies, a French chemist M. Raoult established a quantitative relationship between the mole fraction of a given component and the partial pressure exerted by it. The law states that the partial vapor pressure of each component in the solution is directly proportional to the mole fraction of it in the solution. Now, if P1 and P2 are the partial pressures exerted by the components 1 and 2 at a certain temperature, then, according to Raoult's law, P1 is proportional to X1, or P1 is equal to P1 naught X1, where P1 naught is the constant of proportionality and represents the vapor pressure of pure component 1 at the same temperature. Similarly, for the component 2, P2 is equal to P2 naught X2, where P2 naught represents the vapor pressure of the pure component 2. Now, if you apply the Dalton's law of partial pressure, the total vapor pressure of the mixture would be equal to the sum of the individual partial pressures of the component 1 and 2. That is, P total is equal to P1 plus P2, or P total is equal to X1 P1 naught plus X2 P2 naught. Let this be equation number 1. Further, you know that for a binary solution, the sum of mole fractions x1 and x2 is equal to 1. Or we can write x1 equal to 1 minus x2. Now substituting for x1 in the equation 1, we get P total is equal to 1 minus x2 P1 naught plus x2 P2 naught. Let this be the equation 2. In the equation thus obtained, we can see that P total is a linear function of mole fraction x2 as P1 naught and P2 naught are constant at a particular temperature. If a graph is plotted for the partial vapor pressure of the first component against the mole fraction, corresponding to the equation P1 is equal to x1 P1 naught, then a plot as shown here is obtained. As you can see in the graph, when the mole fraction of first component becomes 1, the partial pressure of component 1 is the vapor pressure of the pure component 1. Similarly, a plot for the component 2 corresponding to the equation P2 equal to x2 P2 naught on the same set of axes is represented as shown here. Now, as can be seen from the curve, the vapor pressure of the pure component 2 is higher than that of the pure component 1. This means that the component 2 is more volatile than component 1. Now the total vapor pressure of the binary mixture P total is given by the sum of the partial pressures P1 and P2. As you can see in the diagram, the solid straight line gives the plot of P total versus mole fraction. Further, as the vapor phase is in equilibrium with the solution phase, the composition in the vapor phase can be determined by the partial pressures of the components by the equation P1 is equal to Y1 P total and P2 is equal to Y2 P total, where Y1 and Y2 are the mole fractions of the components 1 and 2 respectively in the vapor phase. It is important to note that the above holds true only if the two components in the binary solution are volatile and are completely miscible with each other. Now, if one of the components in the binary solutions is considered to be highly volatile, such that it exists as a gas, then, as you know, its solubility is given by the Henry's law, P is equal to kHx. As can be seen from the equation, the partial pressure P of the highly volatile component or gas is directly proportional to the mole fraction x, and kH is the constant of proportionality which can be equated to P naught. In other words, we can say that Raoult's law is a special case of Henry's law. Let us now discuss the vapor pressure of binary solutions of solids in liquids. That is, Raoult's law for non-volatile solutes. A non-volatile solute has no tendency to form vapor at the temperature of the solution, and it will therefore not contribute to the total vapor pressure of the solution. For example, in a solution of salt in water, salt is a non-volatile solute and does not contribute to the total vapor pressure of the solution. Thus, the vapor pressure of the solution will be the vapor pressure due to the solvent only. That is, P total is equal to P1 or P total is equal to x1 P1 naught, where P1 naught is the vapor pressure of the pure solvent at a particular temperature and x1 is the mole fraction of the solvent 1. On the basis of Raoult's law, the liquid solutions can be classified into ideal and non-ideal solutions. Let us first discuss the ideal solutions. A solution that obeys Raoult's law over the entire range of concentration is said to be an ideal solution. For an ideal solution, the enthalpy of mixing and the volume of mixing of the pure components are zero. This implies that no heat is evolved or absorbed, and also there is no change in volume on mixing of the two components. For example, if 50 ml of hexane is mixed with 50 ml of heptane, the volume of the solution obtained is exactly 100 ml, and no heat is evolved or absorbed in the process. At the molecular level, the ideal behavior can be explained in terms of the intermolecular attractive interactions between the two components. If A and B are two components, then in an ideal solution, the magnitude of A-B interactions will be same as the magnitude of AA and BB interactions. However, in real life, there is actually no such thing as an ideal mixture, but some liquid mixtures get fairly close to being ideal. These are mixtures of two very closely similar substances. Some common examples of mixtures that show nearly ideal behavior are hexane and heptane, benzene and methylbenzene, chloroethane and bromoethane. Since ideal solutions obey Raoult's law, they show the graphical behavior as shown here. Let us now discuss non-ideal solutions. Solutions that do not obey Raoult's law over the entire range of concentration are said to be non-ideal solutions. Non-ideal mixtures produce curves rather than straight lines as shown here. The dotted straight lines represent the ideal behavior and the curved lines represent the deviations from the ideal behavior. The reasons for the deviation are the intermolecular interactions at the molecular level. For a non-ideal solution, the magnitude of AB interactions is not same as the magnitude of AA and BB interactions. Also, delta H mixing is not equal to 0 and delta V mixing is not equal to 0 for such solutions. If the magnitude of AB interactions is weaker than the magnitude of AA or BB interactions, then this implies that such solutions have a higher tendency to escape in the vapor phase and will show a higher vapor pressure. Such solutions are said to exhibit positive deviation from Raoult's law. The total vapor pressure of such a solution is greater than the vapor pressure corresponding to the ideal solution of the same composition. For example, a mixture of ethanol and cyclohexane shows positive deviations from the Raoult's law. Ethanol exists in highly associated form due to hydrogen bonding. On addition of cyclohexane, its molecules get in between and there is a considerable reduction in ethanol-ethanol hydrogen bonding. As a result, it becomes easier for the ethanol molecules to escape into the vapor phase, and thus we see the positive deviations from the Raoult's law. For a positive deviation, delta H mixing is greater than 0 and delta V mixing is also greater than 0. Methyl alcohol and water, carbon tetrachloride and chloroform are some other solutions that exhibit positive deviation from the Raoult's law. On the other hand, if the magnitude of AB interactions is greater than the magnitude of AA or BB interactions, the escaping tendency of A and B type of molecules decreases and the partial vapor pressure of each component decreases. This in turn results in the decrease of the total vapor pressure of the solution. Such type of solutions are said to show negative deviations from the Raoult's law. As you can see here, formation of a H bond takes place between the chloroform and the acetone molecule. This decreases the escaping tendency of the individual molecules and results in negative deviation from Raoult's law. For the solutions exhibiting negative deviations, delta H mixing and delta V mixing both are negative. A few more examples of non-ideal solutions exhibiting negative deviations are phenol-aniline and chloroform diethyl ether solutions. A detailed look at the two graphs show that there are some large deviations from ideal behavior at specific compositions. These very large deviations from ideality form a special class of mixtures known as azeotropes or constant boiling mixtures. Azeotrope is thus defined as a special class of liquid mixtures that boil at a constant temperature and at a certain composition. At this condition, the mixture behaves as if it was a single component with one constant boiling point. In such cases, it is not possible to separate the individual components of the mixture by fractional distillation. Azeotropic mixtures can be further classified into two categories: minimum boiling mixture and maximum boiling mixture. Let us first discuss the minimum boiling azeotrope mixtures. When the positive deviations from ideality are sufficiently large, the mixture is said to be a minimum boiling azeotrope. As you can see from the graph, the total vapor pressure of the azeotrope is given by the maximum, represented as O in the curve. Now, as the vapor pressure is maximum at this point, it gives a minimum boiling azeotropic mixture. At this point, O, the concentration of the vapor phase, is the same as the concentration in the liquid phase and is referred to as the azeotropic concentration. Ethanol and water form a minimum boiling azeotrope at 351.15 Kelvin and at a composition of 95.4% ethanol and 4.6% water. Let us now discuss the other type of azeotropic mixtures: the maximum boiling azeotropic mixtures. When the magnitude of negative deviations from ideality is very large, the total pressure curve in such cases passes through a minimum X. As you can see in the diagram, the point X corresponds to the minimum vapor pressure, so this will result in a maximum boiling azeotropic fraction. Nitric acid and water is an example of maximum boiling azeotrope. The azeotropic composition of this mixture at 393.5 Kelvin is 68% HNO3 and 32% water.
Colligative properties are defined as properties of the solution